Okay, so in the current video, I will be discussing about uh, concentration inequalities. So these inequalities will be later on useful when we try to prove regret bounds for the various algorithms. So let me first mention the aim. So what are we trying to achieve at the end of it? Say we are given a distribution, some distribution, say D, whose mean we know, let us call it mu, and whose variance also we know, let us say sigma square. This can be any distribution, it can be a normal distribution or any distribution we want. Now we pick up some identically distributed and independent random variables from this. Let us say xi. Of course, if we pick a lot of random variables from this distribution, we as per the definition of the distribution, if we pick sufficiently many of these xi's, eventually their mean would converge to mu, and eventually their variance would become sigma square. But say we do not have infinite choices, instead we pick m of those. Say we just pick x1, x2 and so on up to xm, and now we want to know what their mean is and how close is their mean to the mu of the original distribution. So we denote their mean by mu m bar. Bar is just to say that it is the sample. So this is the this mu is called the true mean, right? Because it is the correct mean of the distribution, and this mu bar is the sample mean, because this just is depending on the samples we took, the m data points we collected. So this mu m bar is what, by definition, it is x1 plus and so on up to plus xm upon m, just the average of all the data points collected till this point. Okay, so we want an estimate of how close mu is to mu bar. So what is mu minus mu bar or mu m bar is what we need a bound on. And concentration inequalities are of the form that the probability of this is greater than epsilon, that the difference between the two means is greater than epsilon, should be bounded. We must be able to say with some certainty that mu is in some neighborhood of mu m bar, and vice versa, that mu m bar is in some epsilon neighborhood of mu. So we want that the probability, so what does this represent? So let us say this is our number line, and say this is our actual mu. So we can draw a region around it of mu minus epsilon and mu plus epsilon, and we want our actual mu to, we expect our actual mu to be some actual mu bar here to be somewhere in this region. That is what we hope, if we have taken sufficient number of samples from our distribution. So what is the probability that this doesn't happen? What is the probability that mu bar is somewhere in this region? This is what we want to know. Of course, this should be small, and this should be upper bounded by something. Some number should be an upper bound, like we can say that maybe it is less than equal to delta. So this statement means that, of course, for continuous variables you can either put the equal to sign or you may avoid it. It won't matter in the end. But the key thing is that what does this statement say? It says that the probability that the sample mean deviates from the true mean by more than epsilon. On the other side, of course, deviation means absolute values. So the probability that it deviates by more than epsilon is very less. It is less than delta. So we can say that with probability 1 minus delta, right, we can be sure that mu is in epsilon neighborhood of mu bar and mu bar is in epsilon neighborhood of mu. So this is all the interpretation is all about. So our target is to get deltas given several epsilon values. So we will see what all deltas are possible. So just as a heads up, unlike the other videos, here I will keep only the important things on the slide so that it can be used later for reference. So I would be erasing everything which is not necessary, and let us increase the size of it. Okay, or maybe okay, and maybe we can manage. Okay, or maybe we can just select and erase. Maybe let us see. So this is some region I do not want. This was just for explanation purposes. Yes, it works. Okay, so I need to complete a loop. Maybe yes. So up to this point, the only good equation, the relevant equation for us is this one. Oh, okay, so maybe I should be able to draw some hollow shapes, or maybe I can just, okay, so till this point this equation is the one we have, and we want a tight delta. And what does tight mean? Which inequality is better? The inequality which can assure us a tight bound, that is a delta which is small, maybe, because if the delta is small, we can be sure with a, so let us see. So if we have a small delta, it simply implies our confidence is high. Confidence is high that our mu m bar indeed belongs to this range, mu minus epsilon to mu plus epsilon. So all we look for is a small delta. Now through various inequalities, let's first look at the results, maybe, because then, okay, and let me do it with a different color, maybe, because then it would be better. Let us first look at the results which we are going to derive by the end of it. The results are that the possible delta values, okay, so there is a Chebyshev inequality. I think I should have used the white one itself, because this is too, okay, so there is Chebyshev inequality. Okay, 1 minute. Yeah. As per the Chebyshev's inequality, the delta can be chosen to be 1 over m epsilon square. Okay, let me write it down more precisely, because it would be easier to remember that way. So as per the Chebyshev's inequality, our delta can be written as variance of x upon m epsilon square. So all this would fit into this equation. Okay, and let me just write down that mu is nothing but it is the actual expected value of x. So in this case, Chebyshev tells me that the delta, the confidence we can have, that we can be sure that if we take m samples from any distribution and we know the variance of the underlying distribution, then we can be sure that we are correct. That is, the sample mean which I am getting is within epsilon of the true mean with 1 minus delta probability. So we can see that as m increases, our delta decreases, and as delta decreases, we reach the same thing, that our confidence is increasing. That mu m indeed belongs to this region, because this confidence is nothing but 1 minus delta. So if delta goes small, this confidence increases, and delta goes small if m increases. If variance is small, then also we can say that yes, we are more confident, because there is more predictability because variance is small. And if epsilon is large, then also we can be more confident, because what is epsilon? If epsilon is large, we have a larger range to play with, and we can be more sure about, yes, I am, for example, I am not sure for epsilon equals to 0.1 that whether we can agree to such tighter bounds, that mu m lies in within such a tight bound. But say we give you epsilon equals to say 0.5, we can be more sure about that. This is the limit which comes from Chebyshev's inequality. Of course, we will prove how to reach this, but for the moment, we will be doing this just getting the values of delta. So one value is this. There is another value, and that is after centering, we have another inequality, which is something which comes through Chernoff bounds. Okay, and by the way, there is another important thing whenever we apply any inequalities. So this one, the Chebyshev inequality, which I have just mentioned, it comes out of another inequality, which is Markov's inequality. But Markov's inequality is only for non-negative random variables. But in the process of derivation of Chebyshev, the variable chosen by us is already such that it is positive. Basically we choose x minus expected x square, and squares are always positive. So here we don't really need to worry about any cases, right? So for example, this has no exceptions. No, or not exceptions is not a correct word for something that comes out of derivation. I would say it has no conditions. It works everywhere, so it is a very strong bound. There is a second bound as well, which is a bit conditional, and this is called the Chernoff bound. Of course, if we are using something which is more conditional, why to use it if it is not good, right? So it is definitely tighter than Chebyshev. So it is tighter, but conditional. So if you assume certain things, you will get a better bound through Chernoff bound compared to Chebyshev's bound. And what is Chernoff's bound? Chernoff's bound is exponential of minus m epsilon square upon 2 sigma square. or 2 times variance of x, let's say. Clearly you can, okay, and you might put a 2 as well here for the kind of inequality we are discussing. We have a mod, so yeah, this is the exact expression. So a couple of things one might ask is that why, okay, yeah, so why the numerator of this became the denominator here, so, and why and the denominator just became numerator. The reason is that our original logic that if m increases, delta should decrease and the bound should become tighter still holds, right? It is because there is a minus sign as well, and exponential in itself is a monotonically increasing function. So exponential of minus x is a monotonically decreasing function, and when we increase m, this x increases, so this exponential of minus x decreases, so delta becomes tighter. So whatever was true there, that on increasing m, as we intuitively know as well, as we have an intuition for as well, it should decrease, right? Maybe, yeah, on decreasing on increasing m, delta should decrease. That is what our intuition says, that we should be more confident about our predictions because we have taken more samples out of it, and the confidence in our predictions is essentially 1 minus delta, because delta is just the probability that we would go wrong by more than epsilon, and as epsilon increases, this should get tighter. As we expected, our confidence must increase, and variance is the same thing. So you can see that delta here was variance of x upon m epsilon square without any conditions. In Chernoff bounds, this has sort of reversed, that is m epsilon square upon variance of x, just with an additional 2, but an additional 2 appears here as well, and we put it in exponential of a minus function, a negative exponential. So these are the two bounds we are interested in. I think with these two bounds we are through. Now the condition which we need to discuss is what was the we can say the conditional thing in Chernoff bounds, and that is our variable, a random variable, or the distribution, because random variable is anyway coming out of a distribution. So our random variable or the distribution, it must be belongs to, you can say, sub-Gaussian, either sub-Gaussian or Gaussian. If this condition is satisfied, that our distribution or random variable is either sub-Gaussian or Gaussian, we are through. Chernoff bound holds. But if the underlying distribution or if the random variable is not sub-Gaussian or is not Gaussian, then Chernoff bound won't hold, and our best bet is through Chebyshev's inequality. Okay, so that does it. Now all we need to do is to look at proofs for both of these. Let us start with Chernoff. Let us start with let us wait a minute, okay, so let us start with the Chebyshev's inequality first. So there is an entire algorithm as to derive Chebyshev's inequality, and it all starts with Markov's inequality. And again, in our bounds we don't really need Markov's inequality, it is just for derivation purpose. But the Markov's inequality is that probability that x is greater than or equal to an epsilon, which is some value, okay, not equal to, very sorry, greater than equal to epsilon is less than or equal to the expected value of x upon epsilon. And there are a couple of conditions here. One, x is positive random variable, and 2, epsilon is positive. With these two conditions, we have this Markov's inequality. So what is the intuition for this? We have some x which is positive, right? And the distribution of x, it peaks at expected, say this is our x. So if we take the mean, it looks like say this is the probability of x, and say this is x, probability that x is equal to a small x, and say this is a small x. So what do we see? That roughly this is the expected value of x. So we say that if we deviate, if we took some epsilon which is high, say here, then what is the probability that x is greater than that epsilon? Well, it increases as expected value of x increases, because if the expected value of x is higher, there is more chance that we will cross epsilon. But as epsilon increases, this probability decreases, because of course if it is farther away, there is less chance that we exceed epsilon. So but it has some underlying proof as well, of course, which I am not worried about right now. But the fundamental thing is that probability that x is greater than or equal to epsilon is less than or equal to expected value of x upon epsilon. And now to get to Chebyshev, all we need to do is to put x equal to replace instead of putting x equal to anything, let us do this, because x cannot be equal to x minus something, right? So just the better term is substitute x for x minus expected x. The whole square. Let us see whether this is a valid substitution or not. Okay, and another substitution is that choose epsilon to be epsilon square. Okay, so let us see whether this is a valid substitution or not. Okay, let me write it down a bit more clearly. This is square. Okay, so we wanted, there were two conditions on Markov's inequality, right? Markov's was that probability x greater than equal to epsilon is less than equal to expected x, and upon epsilon there were two conditions there. One was that x must be a positive random variable. If we take x as x minus expected of x, it might be positive, negative, 0, whatever. But if we take the square of it, x minus expected value of x square, that is definitely positive. So that condition we are satisfying. Is it a random variable? Yes, because x is a random variable. So x minus a constant is also a random variable, right? It can take any value, which x can take, minus a constant, and then therefore its square is also a random variable, because it can also take any value, because x minus c is a random variable, so x minus c square is also a random variable. So the first condition, that x is positive random variable, this is definitely satisfied. Epsilon is positive is again satisfied because we substituted epsilon with epsilon square. Now epsilon, if it is real, then epsilon square has to be positive. So both the conditions are satisfied. Now imagine putting these conditions into Markov. So so what happens? X greater than or equal to epsilon becomes what? X minus expected x, the squared, and then greater than or equal to epsilon squared. And well, this is equivalent to saying that modulo x minus expected x, we are just taking a square root on both the sides, so we get this should be greater than or equal to epsilon, where epsilon must now be positive. Here there were no conditions, but here if you want this to be satisfied from here, you definitely need epsilon to be positive, because you take the square root, you will get mod epsilon, and mod epsilon is equal to epsilon only if epsilon is positive. But here because both the sides are positive, if a is greater than b and a and b are both positive, we can definitely say that a square is less than equal to b square as well, because a bigger number times a bigger number is still bigger than a smaller times a smaller number. So that condition is satisfied. Note that if epsilon were negative, it won't be true. Like 3 is definitely greater than or like 1 is greater than equal to minus 2, but 1 square, which is 1, is not greater than or equal to 4, which is minus 2 square. So epsilon needs to be positive, but if it is positive, we can just take the square root on both the sides, because greater than equal to will then be monotonic, right? So anyways, so this is the first part we have. I think we can erase this part, it's not really needed. Okay, so with this, what does RHS now become? What is expected value of x? Oops, what is expected value of x now? RHS, it just becomes expected value of x minus expected value of x square. Well, that is simply the variance of x, and upon what is but yeah, there is a trick, there is a slight trick. Oh no, it's fine. So variance of x upon epsilon square is what we get. Yes, fine. So having done all this, what do we get? At the end of it, we get something like probability of modulo x minus expected x greater than epsilon is less than or equal to variance of x upon epsilon squared. But what did we originally wanted? We didn't wanted x, we wanted mu and mu m. Mu we somehow have because expected value of x is mu, but we, instead of x, we wanted mu m bar. So let me just introduce two small things. This is an aside which would be helpful to proceed ahead. One is that variance of x plus y is equal to variance of x plus variance of y. right? This holds if x and y are independent. And the second thing is that variance of ax, because of the nature that variance involves squares, variance of ax is simply a square variance of x. So these are the asides, and then there is third thing, which is linearity of expectation. These are standard results in probability theory, that expectation is linear in the sense that expected value of sigma xi is equal to sigma times expected of xi. And there are no ifs. There are no ifs here. This is a small aside which we have with us. So we will be using this to prove certain results here. What those results are: that we have that the probability of x minus expected value of x greater than epsilon is less than or equal to variance of x upon epsilon square. What do we want? We, just like we did one substitution here, we need to do another substitution here, that x, now we want to replace it with mu m. And as we can see that this substitution would give us the required inequality in terms of mu m. So if we put x as mu m here, what is the expected value of mu m? Okay, so let me just indicate it the same way I did above. The indications are consistent. So if we do this, what do we get? What is expected value of x? It indeed what is the expected value of mu m? Very sorry. Well, if you do use this linearity of expectation thing, it is simply 1 over m times expected value of x, and in the numerator everything gets added, so times m, and that remains expected value of x. So this part becomes mu m minus expected value of x. On the right hand side, what is variance of mu m? For the variance of mu m, as our variables are I, d independent, so we can use variance of x plus y as variance of x plus variance of y. So it is basically simply variance of xi upon m and summation over I, and this is simply a square. We can use ax equals to a square variance of x, so you get 1 over m square times variance of x, and this, when you put back here, gives you the result we had, variance of x times m, which is basically, sorry I missed that, so which is basically variance of x upon m. And this, when you put back, you get probability that mu m minus expected value of x greater than epsilon is less than or equal to variance of x upon m epsilon square, which is what was the Chebyshev's inequalities delta. So we have proved this, and we have not used any additional constraints here. Okay, so we move ahead maybe. Yes, so we have proved one of these, that is the Chebyshev's, which is delta is variance of x upon m epsilon is squared. We want also to prove Chernoff bounds, but I see the present video is a bit too long, so maybe, but anyways, let's see. Markov's inequality is like the melting pot of all of these. In the Markov's inequality itself, you just replace x with e to the power lambda x, and you take epsilon, you keep it as epsilon just greater than 0. Now let us move back and look at whether it is satisfied or not. So let me just zoom out. You can see that what were the restrictions on Markov. The first was x is positive random variable. If we take exponential of anything independent of lambda, it has to be a positive thing, right? Because exponential is positive, and because x is a random variable, can take any value, e to the power lambda x also can take all the values, you can say randomly, right? A bunch of values randomly. So it is a positive, and it is positive, and it is a random variable. Further, epsilon is positive by choice, so we can see that yes, we can apply a Markov's inequality on this random variable too. So let us do that. Just default it to 100, and let us now try and apply Markov's inequality on this. What is LHS? What does x greater than equal to epsilon now entail? It means e to the lambda x is greater than or equal to epsilon, right? No, so I think I messed it up a bit. What we do is that we take, maybe instead of substitution, to get to Markov's inequality, we don't really substitute. So this is a key thing here. There is no substitution. Earlier there was a substitution, right? We put something in terms in place of x. We take as in assign y equals to e to the power lambda x. So y is also a positive random variable, and we have y equals to this. So what happens? X greater than equal to epsilon then is simply equivalent to what? If assuming lambda is positive, let us assume this is another assumption we are taking. So if x is greater than equal to epsilon, then lambda x is greater than or equal to lambda epsilon, right? Because lambda is positive. We have used this fact here, which would further mean that because the exponential is monotonic, e to the power lambda x is greater than or equal to e to the power lambda epsilon, because it was monotonic. Further, as y is equal to e to the lambda x, we have y is greater than or equal to e to the power lambda epsilon. So the probability that x is greater than or equal to epsilon is the same as the probability that y is greater than or equal to e to the power lambda epsilon, right? If we substitute y equals to e to the lambda x. Note that in the previous case, while trying to get the Chebyshev bound of variance of x upon m epsilon square, we were substituting something. So we had x here, and instead of x we were substituting x minus expected x, and then we finally replaced x with mu and so on. Here we didn't substitute anything. Here we assigned a value to y, that let us say it is e to the lambda x. It was not put back into the equation as e to the power lambda x greater than or equal to epsilon. We used the bound on x itself, that x is greater than or equal to epsilon, and used it to get a bound on y, right? Okay, now the interesting thing is our RHS. Whoa, wait, sorry. Yeah, now the interesting thing is our RHS. What does RHS become? Well, RHS now becomes expected value of x upon epsilon. So expected value of x you know what, there was a better way to do all this. I just realized, in fact that is why I was trying to record these, because sometimes when you think on it for a second time, there are interesting ways to do it. Let us remove all this. Oh my god, yeah, this is a better way to do this all. Just remove everything. Yeah, so a better way to prove this is actually again by substitution. What do you need to do? You just substitute x with e to the power I was just thinking about a way to make this quick. Nope, I think that was the better way. So you take y equals to this and I mean, this is a really interesting proof, because there were two tricks. So let me say this is trick 1, right, which you need to remember. Basically you cannot just come up with these ideas in real time. These are difficult to come up with. So the trick 1 was that you used y equals to e to the lambda x, and then you substitute x is greater than or equal to epsilon, and you get that is equivalent to y being greater than or equal to e to the power lambda epsilon. And then there is a trick 2, that you do not actually calculate the RHS, and this is a very interesting trick. I had missed it when I was giving it a first read. Very interesting indeed. So here the trick is that you basically do it this way, that you say that okay, we have found something, that probability of x greater than or equal to epsilon is the same as probability of y being greater than or equal to e to the power lambda epsilon. Why? Because we just proved that x greater than equal to epsilon is the same as lambda x being greater than equal to lambda epsilon, and taking exponentials this simply becomes y, which has now a lower. So probability of this happening is equal to the probability of this happening, and now instead of applying something on this, the trick here is to use this. This is being used, this is not being used, and apply Markovs on this. This is on this, apply Markov. This was just super interesting. Apply Markov on this. So now y is a positive random variable. E to the power lambda epsilon by definition is positive because exponential is positive. Y is a positive random variable by definition because it is e to the lambda x. So this thing can be used to apply Markov on, and we know that this will be less than or equal to expected value of y upon e to the power lambda epsilon, right? And what is expected value of y? It is expected value of e to the lambda x, which is simply mgf, moment generating function of x, because exactly by definition mgf of x is expected value of e to the power lambda x. So that gives us mgf of x. So see the very subtle thing which went into it. We wanted to get expected value of y, so our target was to get expected value of e to the power lambda x, because that is something which is known to us, that is beautifully known to us, because that is simply the mgf of x. So we wanted to get e to the power lambda x expected value. For that we put y equals to e to the lambda x, so that we may hopefully end up with expected value of y sometime ahead. But to get y here, we needed to have y here as well, and to have y here, what can we do? We can use this thing so that eventually we get a bound on probability of x greater than equal to epsilon. So we have just now, you can see this was pretty interesting. We connects x to its mgf, right, which is very interesting. In fact, now given this result, I will make a separate table as well. So I will just get these results once I am done, but I will make two tables in the end of it, at the end of the video, relating everything, right? But for the moment we have that probability of x greater than or equal to epsilon is less than or equal to mgf of x, because it is e to the lambda x expected value upon e to the power lambda epsilon. Now we have one more thing, that this video is getting a bit too long, so what I will do is maybe I will stop here and make a separate video with concentration inequalities continued, and there I will summarize the results as well. So maybe that will be a better idea. Let me end this video here, and you can give your feedback anyway on this video. Thank you. Yes.